In this video, we're looking at an interesting integral that popped up for me recently in the context of a larger problem. It's the integral from 0 to 2 pi square root 1 minus cosine t dt. Now, the first solution method that occurred to me was to use what I'll call the conjugate method on this integral. And something really interesting happens when you take this approach to the integral. If you aren't extremely careful about what you're doing with plus and minus signs, when you evaluate this integral, you get 0. And I know that's impossible because the integrand of this thing is always non-negative. It's got to come out to a positive answer. So I'll discuss sort of what goes wrong and how to fix it. Then we're going to look at a different approach to the integral that I'll call the trig identity method. It's just a different trig identity that cleverly bypasses the sign issues from the first method. So here's the basic idea of the conjugate method. I want to build a 1 minus cosine squared inside of a square root because I know there's an identity that can reduce that to sine squared. So I'm going to multiply top and bottom by the conjugate. Then I go ahead and multiply the interiors of those two square roots in the numerator, and that's a difference of two squares by design, and I'm going to get a 1 minus cosine squared inside that square root. Then we simplify the 1 minus cosine squared to a sine squared, and then I have the square root of sine squared. Now we're used to, in so many problems, just simplifying that to the sine of t. But I'll give you a warning that this is where our tricky sign issue is hiding today. First, let's see what goes wrong if we don't notice that. So I'm going to manipulate the integral a little more just to highlight how the chain rule is working backwards here. I'm putting a minus sign on the sine t because that's the derivative of the interior of the square root piece, and then I compensate it out in front with another minus sign. All right, so I have 1 plus cosine of t raised to a power right next to the derivative of that interior. And I'm ready to guess the antiderivative, so I add 1 to the exponent, divide by the resulting number. So this gives me a 1 plus cosine t to the 1/2, divided by 1/2, which is the same as multiplying by 2. And I've got my antiderivative. And now I see a serious problem. If I plug in the upper limit, the cosine of 2 pi is 1, and I end up with negative 2 root 2. And then I subtract what I get when I plug in the lower limit, and again the cosine is 1. The cosine is periodic with a period of 2 pi. So I've got to get the same number for the upper and lower limits, and these are going to add to 0. Well, this is impossible because I have the integral of something that's always non-negative. I know I need to get a positive result. So as I already said, the gremlin that's lurking in this problem is a really tricky sign issue that occurs right at this step. If I look at the square root of the square of the sine function, I know that that has got to always be a positive number because I'm squaring the sine function, which gives me guaranteed a positive number before I square root it. In fact, the square root of the square of something is really just another way of saying the absolute value. So it takes whatever value is there and erases the minus sign. So really at this step, I should have said it's the absolute value of the sine function. I'm guaranteed to get a positive result. And on the interval 0 to pi, there's no difference between the absolute value of sine t and sine t because the sine function is positive. Once you cross over to the interval from pi to 2 pi, then the sine function becomes negative, and I have to write the absolute value as the negative of the sine function. So the way to proceed with this integral is to actually split the integration interval at pi and do two separate integrals. So we'll go ahead and erase our work from before. And we're going to split the integration interval. So I go from 0 to pi sine t over square root 1 plus cosine t dt plus the integral from pi to 2 pi of negative sine t. Again, the sine function is negative on that interval, so negative sine t is positive. Now the actual symbolic manipulations to get the antiderivative, we've already done it once before. So on the first integral, I throw in a minus sign to get ready to guess the antiderivative, put a minus sign out in front. And now I have the derivative of the interior of this thing. And I just use the power rule, and I get negative 2 square root 1 plus cosine t evaluated from 0 to pi. And my second integral already comes with the minus sign that I needed inside the integrand, and so I can go ahead and guess the antiderivative. So in the first piece, when I plug in the upper limit of pi, the interior of the square root vanishes because the cosine of pi is negative 1. And when I plug in the lower limit, I need to subtract that. So I'm going to get a plus 2, and then the square root of 1 plus cosine 0. Cosine 0 is 1, so I have 2 root 2. Then in my second piece, I plug in the 2 pi for cosine in the upper limit. Again, the cosine of 2 pi is just 1, so I end up with 2 root 2. And then in my lower limit, I have a 1 plus cosine pi, which is 0 inside that square root. So in the end, I end up with 4 square root of 2 for the value of this integral. All right, so let's look at a method that bypasses all of these issues entirely. And the idea is to just find a different trig identity to simplify the interior of that square root right in the first step. So I want to remind you of a really useful trig identity. When you have the square of a sine or a cosine, these identities can be immensely useful. So when I have the square of a sine function in particular, that's 1/2 times the quantity of 1 minus cosine of twice the angle. And what I notice in this identity is the 1 minus cosine of something is related to a square of a sine function directly. Well, this means I might be able to change the interior of my square root to just the square of a sine function. So I'll go ahead and multiply both sides by 2. And now I'll just replace theta with t over 2, and I end up with 2 sine squared t over 2 is equal to 1 minus cosine of t. So I'm going to replace 1 minus cosine t in the integral with 2 sine squared t over 2. And the square root undoes the squaring inside of that. I'm also going to pull out a factor of square root of 2 out in front as I'm going. And at this point, I want to highlight that same sign issue. Can we really just say the square root undoes the squaring without worrying about these absolute value bars like we did in the last example? And the fortunate thing about this approach to the integral, if I look at the argument of the sine function here, that's t over 2. And if I go to my upper limit of integration, I'm only getting to the sine of pi. In other words, we're staying on that first half of the first period of the sine function where it's always positive. And that's why we get away with just ignoring the sine issue this time. So to get the integral done, I set up to make the chain rule backwards easier to think about. So I need a 1/2 in here, and I'll compensate with a 2 out in front. That 1/2 is just the derivative of the argument of the sine function. It makes it easier to see the chain rule backwards. So I have a 2 root 2 out in front. And then the thing I differentiate to get 1/2 sine t over 2 is negative cosine t over 2. The derivative would undo that minus sign, and the chain rule would produce that 1/2. So when I plug in the upper limit, I get negative cosine pi. So negative negative 1. Then when I plug in the lower limit, and I'm subtracting that, so I've already undone my minus sign here, I get the cosine of 0, which is 1. And 1 plus 1, of course, is 2, and 2 times 2 is 4, and I end up with the same value, 4 root 2. Okay, so this comes out to 4 root 2. And for those of you who are curious, this integral popped up when I was computing the arc length of the arch of a cycloid function. And I'll post a link real quick to that arc length video if you're curious to see how this integral came up in the context of a larger problem. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.